Hello, my name is Barry. I'm a PhD student at the Technion in Haifa, and I would like to talk to you about the probability distribution of the astrophysical gravitational-wave background. This talk is based on a paper that I wrote with Vincent, Desjacques, Reischke, and Hagai Perets, and which you can find on the archive, for example, if you scan the QR code that I provided here. Now, the gravitational wave background is the sum of all gravitational waves that arrive at a given detector at a given moment in time from all over the universe. This background is a random background because the phases of those gravitational waves are essentially random, and also the properties of the sources are distributed according to some probability measure. For example, an initial mass function in the case of binaries. This background, as far as I'm aware, has not yet been detected, but it is hoped that it will be observed by LISA and also by other examining cross correlations of ground-based detectors, although it hasn't been found yet. Here I'm going to focus on the contribution of compact binary mergers to this background only. Now this is important because compact binary mergers have the same frequencies as some primordial gravitational wave backgrounds, such as phase transitions possibly, and it is important to disentangle the contribution of binaries from the total signals so that one could detect the cosmological signals. The astrophysical background, I mean the background due to binaries, is also important in its own, on its own. So it can be used to learn about the properties of binaries throughout the history of the universe, about star formation, and so on. So previous studies of this astrophysical gravitational wave background have mostly assumed that it is a Gaussian random field, and they have calculated a quantity called omega GW, which is the energy density of gravitational wave backgrounds. Now, I would like to examine this assumption of Gaussianity and also to calculate not only the energy, the average energy, but rather the full probability distribution. So the way to do it is to add up all the waves. This is done by assigning a complex number z to each wave, whose modulus is the amplitude of the wave, and its phase is the phase of the wave. And then the sum of all waves is just the sum of all those complex numbers. So you start with the first wave from the first source, and then you move on to waves from the second source, the third, fourth, etc., till the nth source, where n of t, it's a function of time, it is the number of overlapping sources at time t. So there are n sources from which waves arrive at the detector at time t. Okay, and then the probability distribution of the signal is just the position of random walker in the complex plane after n of t steps. And this is how we will calculate this. Okay, so the sources are assumed, as I said, to be binary black holes or neutron stars, and the waveform that those sources generate is assumed to depend on a certain amount of parameters, such as the chirp mass, initial semi-major axis, age, etc., which I will collectively call psi, and they are randomly distributed according to some probability measure, which is assumed to be the same for all sources. Of course, all the sources will have different probability distributions for example, masses, but this is taken into account in the probability distribution of the formation times. Okay, so I assume that all sources are identically distributed and independent, and that they are homogeneously distributed in the volume accessible to the detector, with a mean number of overlapping sources given by n naught, and that they are Poisson clustered. This is justified because the correlation length of those sources is much smaller than the mean distance between them. Okay, so if one does a simulation, a Monte Carlo simulation, as LIGO and Virgo did in 2018, then one finds that the plot of the strain H at the detector as a function of time due to the background looks something like what you can see in this plot. So there is a mean 0 and there are some fluctuations, random fluctuations around this mean. And my purpose here is to present a way of characterizing these fluctuations and finding the probability distribution. Okay, so because they are independent and using the argument from random walks that I've explained before, one finds that the probability that the sum of all gravitational waves is, the sum of all strains is equal to h is given by the inverse Fourier transform of this quantity e to the n naught times g of s, where g of s is the expected value of e to the ish from one single source, where I use expected value to mean average over all the probability measure, over the whole probability measure of the source parameters. So this is a complicated integral in general, but it can be done numerically and it can be estimated analytically, as I will show you. And then in this integral, in this calculation of g, only waves whose frequencies are in the detector's frequency range are allowed, are included. Okay? A little bit about the astrophysical model which we use. We adopt the reference model of Cousin et al. From 2019, who studied the different astrophysical models and their effect on the background. This model is rather simple because the main purpose here is just to exemplify the technique to calculate the full probability distribution. It's not really important to use a very, very accurate model. However, if one wanted to use a more accurate model, then of course it is possible. So the source parameters are A, the formation time, the chirp mass, and of course the initial chirp mass has to be related to the final chirp mass through an initial to final mass function. So we use Erpig's law for the semi-major axis, initial one, probability distribution of the formation redshift given by this quantity, well, proportional to this quantity, so it decays exponentially in redshift. We use a Krupa mass function for the initial masses of each binary member. And then we use, for the initial to final mass function, we use analytical fits to stellar evolution simulations given by Frey et al. And Ma et al. Then we need also a halo mass function, and we use a Tinker et al. Mass function. Okay, this is not very important for the qualitative properties of the background, as I shall show. Okay, so if you take the whole model and you calculate g, then you find what is shown in this figure. So on the x-axis there's s, which is the Fourier transform variable, and on the y-axis you can see g of s. Okay, and then we also evaluated it analytically at small values of s. This is important because by the Paley-Wiener theorem, the behavior of g of s at small s dictates how fast p of h, which is the probability of the strain, decays with h. So one can show that g of s goes like s squared times some negative number plus some number times absolute value of s cubed, and this is an irregular part, so that means that p of h will decay as h to the minus 4. And indeed we find that p of h decays as h to the minus 4, specifically it is given asymptotically by this quantity at large values of h. So you see a universal power law which does not depend on the specific astrophysical model, and also does not depend on the number of sources. The only thing that does depend on it is the coefficient B, which is really the mean single source cubed amplitude at the origin. Okay? Right, so computing G numerically and then doing the Fourier transform exactly, one finds that this is how P of H looks like. So on the x-axis you have H normalized by the mean absolute value strain, and on the y-axis you have the distribution of x. So you see that at low values of x it is rather flat, and then there's a transition to the power law which I've shown you in the previous slide. If you try to fit a Gaussian, then it fails at large values of h. Okay. Interferences between signals are very important because they affect the low luminosity part. So if one computes the energy of the gravitational waves, which is roughly given by h squared, then you see that if you add up all the energies, you get something that's correct at high values of h, but you miss it very badly at low values of h, and this is because interference has changed the form of the probability distribution. So remember that the gravitational wave luminosity is the square of the sum of IID random variables, which is not a sum of IID random variables. Right. We would also like to remove bright sources, so we remove them by requiring that the signal to noise ratio is below a certain value. This ensures that that G we use does not include sources or gravitational wave events that are resolved by the detector and hence not counted as the background. So we essentially have a certain function of the source parameters which we include as a Heaviside theta function to be lower than some threshold. This introduces a scale h cut, after which the background is very unlikely to have any amplitude, and indeed it would give an exponential decay at strains larger than h cut. Computing this at low thresholds for numerical reasons, for computational complexity reasons, we find that indeed for k equals 10 there's a transition from the flat bit to the power law, and then at roughly h cut there's another transition to an exponential fall off. Okay, so we have identified three regimes. The first regime is one where there's a Gaussian central limit theorem like convergence. Then the second, which is below n0 times hc, okay, only there we see an effective pointwise convergence to the central limit theorem, which does not strictly obtain because the variance is infinite, but nonetheless below n0 times hc, P of x behaves like the central limit theorem. Then in the middle regime between n0 hc and h cut, the power law that I've evaluated before holds, and above h cut there's an exponential fall off, which can also be estimated analytically and matched with a realistic cutoff. Okay, so for LIGO-like sources with our model, we find n0 is roughly 15 and hc is roughly 10 to minus 25. Right, so the conclusion is that I've shown you how to calculate the full probability distribution of the gravitational wave background, that there's a universal scaling at large strains, and that this distribution is non-Gaussian. This can be extended to frequency space, and also in the future we will do it for an inhomogeneous background for LISA. Thank you very much for listening.